We are an institute that works on the cosmos, as the name indicates, and the gravitational wave astrophysics is a must for any leading institute in the world. So our group is somewhat young, has not such a long history as the people in the other side of this panel. It was formed around three existing teams working in several related subjects: gravitation, black holes, neutron stars, etc., etc. And those groups got together to form a more consistent gravitational wave group. And as an institute, we fully supported this move, and gravitational waves have become a strategic line in our strategic program. And we included them, the gravitational waves, in our latest successful Maria de Maeztu application. And after winning this Maria de Maeztu, we have been providing to this group strong support in terms of budget, but also synergies and cooperation with other groups at the Institute. The group has undergone a strong consolidation in the latest years, in the last 5 years. The leader of the group is Mark Gilles. The picture is on the screen, and Mark sends his apologies for not being able to be here. He would be a better representative of the gravitational waves at the Institute than myself. But here you have him and the main members of our group and the areas where they work. As you can see, we have a good varied activity on science, but we also, our technological unit is also making contributions to the gravitational wave sciences. We have active collaborations with several other groups. Here you have a picture of our European collaborations. There's an important one missing here that I will mention later, Eugenio. And our main strongest collaboration is with a group at Valencia, with which we have a coordinated project in the Plan Nacional. And we are strongly cooperating with them. We have established very strong ties, especially around Virgo. More than that, and a bit more locally, we have recently become one of those consolidated groups of the Generalitat de Catalunya. We were awarded one of the groups of Recerca Emergents funding, and this Group de Recerca Emergent consolidates not only our gravitational group in the Institute, but also collaborating groups in the Institute, especially the group of electromagnetic follow-up led by Nadia Blagodornova. So this enlarges the existing group and widens the collaborations inside the Institute. We are members of the Virgo Consortium since 2018. We have been full members since July 2019. Right now, 15 of our members are members of the consortium, and we contribute 5 FTEs, and we are working to enlarge this contribution to Virgo. And our contributions mainly are focused on data analysis. We contribute to the analysis of in the pipeline of data processing of Virgo, and we are also contributing in the technical side, computing and software engineering. We are also keen, we have also been keen to join the Einstein Telescope effort that has been introduced. We have been collaborating with Mario, and I have a pending meeting with Eugenio here to discuss the strengthening of the collaborations between the ICCUB and the IFAE around gravitational waves in general, but also specifically around Einstein Telescope, which I think is a very, very serious project for the future, and where we, by all means, would like to be part of. We are interested in several world packages, and we would like to contribute both in the technological and scientific side. And that's it. I think we are roughly in time. Thank you. So, we move now to a more open part, and we have more or less agreed on a few subjects, but this is going to be an open exchange about 18 minutes. We have eaten a couple of minutes out of the allocated 20. So let me start with history. You have done a nice historical introduction, but there's more to that. So feel free to elaborate on you have started. But I have a question. I heard, if you can please confirm if it's true, that it was probably in the 60s or 50s some skepticism on the real existence of gravitational waves. How did we manage to go from something that was doubted to exist to a full experiment like LIGO and Virgo?
This is an interesting story because it explains how science proceeds sometimes with many doubts and failures. And Einstein himself, at a certain point, this is very known, have doubts about the real existence of gravitational waves and of course of the measurability. Like if with a change of coordinates, really they disappear, these waves. And actually it took some time, and there was a moment, topical moment in 1957, a Chapel Hill conference in which all the Gotha of the physics and gravitational physics in particular met. There were Wheeler, there were
Pirani, Bondi.
Weber, of course. There were Feynman, Pirani, and many. And there, I mean, with a simple discussion, they realized that actually the arrival gravitational wave should allow to distance two points in space. Then if these 2 points are, for instance, two mirrors, then the a laser and a mirror, then the light going back and forth change the travel time, no, during. Or if you connect these 2 points with a spring, then the spring should elongate and compress. So the measurability was, there was a consensus on the fact that actually they could be measured. And Joe Weber at the time was present there. He was a PhD of Wheeler, and he wanted to start an activity. He was a kind of man with fully dedicated to something. No, he dedicated to the Maser invention before, for instance. This was not recognized to him, but he was like a sort of a fool. Sometimes fool open the ways that then wise people follows. No, and he was that kind of man, and he tried with a piece of metal initially, and then also with laser. He tried methods to detect the gravitational wave in a time in which there were no apparent sources able to give a real event. And then he claimed to have detected the gravitational waves, but was not true. And of course, he was then put outside a little bit the scientific community for that. But you should give credit to him that he started really the field. And then when the others joined and were looking to the fact that actually they were not so easy to detect, they continued this activity. People coming from other experience, they went back to their original experiment. They continued the gravitational wave field until progress by progress we arrived to the discovery.
And then we're right to the discovery. And Alicia was mentioning while we were in the technical room, with the microphones, that you successfully predicted the date of the discovery of first gravitational wave, right?
Yeah, right. I would say that people usually is wrong, and then but you can make fun of things a posteriori. I mean, Einstein not always is right. Einstein was wrong a few times. So Einstein tried to publish this paper in 1936 with Nathan Rosen, basically forbidding the real physical effects of gravitational waves. Also, well, he was never sure. So then he was also doing calculations about the amplitude of gravitational waves, but early in 1916 or whatever, and then the amplitudes were really weak because his concept was just the solar system. I don't think that at that time there was even the concept of galaxies or anything. So, and of course, early enough you don't have an idea of, well, you have to wait until the 60s. so that black holes and neutron stars pass from just mathematical entities to physical entities. And then there is all this story of the bars, crazy Weber, but Weber really was a pioneer. He opened the field in order to confirm his findings. There were 18 bars around the world taking data, and then there was the network of the first international network of resonance detectors that was really very successfully operating. Then there was the conscience that we need to study sources. Then part of the Pyrenees, Kip Thorne and others were really studying the sources, and the sources typically classified in these 4 categories. Then came the first generation of the detectors with LIGO, and TAMA, GEO, and Virgo, that were successfully operating between 2002 and 2010. And then comes the LIGO upgrade, because LIGO was designed in a way that basically the first generation was just the proof of concept. And then given the event rates, well, one is the event rates or the expected rates that you present when you ask for money, and the other one is the numbers that we're having at hand. And it was clear to us that you have to wait to this second generation of detectors. The second generation of detectors was delay. It's always delay. So I don't know, it was the 14th of September, I don't know of what year, that appeared in a newspaper that I said, like, in 2015, we will be detecting gravitational waves. And in 2015 should have been the second or the third, no, I think the third, it was the planning of the third observing run of these advanced detectors. Because, well, when you go to space, everything should work, because you cannot go there with a screwdriver. It has to work from the beginning. Here we put the light in the detectors, but it requires a lot of commissioning and several runs until you reach the design sensitivity. So I would have never thought that the day that you put the light in the detectors, you would detect the gravitational waves. I would have to wait until you have to do 2 or 3 upgrades. So I was thinking, like, well, in the planning, 03 will be 2015, and therefore I predicted 2015. So I was wrong as well, so I ain't saying wrong, I'm wrong, because we were so delayed that 01, the first observing run of the fast LIGO, started in September 2015. We were in engineering run, and that 14th of September, the day that I appeared in the newspaper many years ago saying the year, predicting the year, there was the first light. And if going back to history, I mean, in going back to the figure of Alberto Lobo really was a visionary. He realized that this was a very amazing science. He was really working with Italian groups with resonant detectors. I also remember being a PhD student and going to his office, and he was showing me this piece of wood that many of you might have seen, the Loboedro, and that I think is officially called the Loboedro in a journal. And I guess I am in this field just because of him. So we were both PhD students in 1995. We both went to a summer school in Aberdeen, Scotland, whiskey distillery, well, yeah. And he was giving a talk, gravitational waves, and I just said, yeah, my theoretical cosmology is very nice, but I want to devote my rest of my life to gravitational waves. And I finished the PhD and I just jumped into gravitational waves. So thanks to him, there was another group getting devoted to that, and after the detection of gravitational waves, I mean, ICE was representing space, the main contribution, a very important contribution in space. We were the only ones on ground, and now it's amazing the number of groups now being involved in gravitational space in Spain itself. So I'm not sure.
Yeah, so indeed moving to the future and present future and to space, let me mention that I also had the pleasure to work with Alberto Lobo, and he directed the work I did simulating neutron stars. It was a learning experience, but he didn't mention to me, at least, gravitational waves. It was probably a bit too early, and I didn't go that path, but a pity. But as you said, space is the next frontier for gravitational waves.
Yeah, well, let me add to this thing. Alberto happens that he was not working in gravitational waves, but then at some point he did a sabbatical. We went to visit Cardiff, where was one of the big experts in this, and then from there he establishes all the connections with Italy, and then he worked in everything, in the bars, in the ground base, in the space base. And yes, so the space base, I think it's a complementary effort. It's not that it's the future. The future is going to be also Einstein telescope and whatever other things people have in mind. There is also pulsar timing arrays, actually, this is something that is very sad because nobody in this country is working in post-terminal arrays.
But
nobody
the
works in
leader,
post-terminal
but the
arrays,
leader
no.
is Spanish.
Eh?
But the leader, Xavier Siemens, actually is
Well,
Spanish.
the leader of one of the consortiums in the US, so
In the
it
US.
doesn't count. No, actually, probably they are going to make an announcement soon, a very interesting announcement. So it's a pity that nobody got interested in this. So I think, despite the fact that in Spain there has been a significant development, I mean, as Alicia said, 10 years ago we were basically in Mallorca and ourselves in Barcelona, and some people doing some theory, and still the situation hasn't improved too much. Actually, now that we have IFAE. We have other groups, but they are not very. We have UV too. Actually, we expect that UV will help us in the data processing for LISA, right? But there are not really big developments in Spain, right? And this is a pity because I think now is the time to make a real, getting inside this because of all those opportunities. LISA, Einstein telescope in the ground. There are pulsar terminal arrays. There are also other experiments for CMB polarization. There are many things going on.
I would like to add things like, let me be nasty with my own collaboration, because the glory was given to LIGO because they were the first, they were doing the first detection. Anti-LIGO is the American experiment. But actually all the technology in which is based the success of LIGO, it was basically developed in Europe. It was basically developed from the GEO group, so the German-British collaboration, and also the Virgo group, all the Virgo groups involved. And that was the technology that was being exported. They were the largest, they were the first. But all the technology has been developed, mostly the leaders were in Europe. And now some of these leaders, now we have them in Spain. And now they are, our theoretical groups are not just theoretical, they started with the effort of IEEC and ICE, getting into hardware, and now there is more interest in this field in hardware, IFAE, CMAT, and then the smaller groups that they can contribute to smaller sensors and so on. So I just hope that this will be a bright future, still in Europe, still in even more in Spain, and now having that one of the spokespersons of a collaboration, of the future ground-based collaboration, is just sitting next to us. I think Spain, Catalonia has a great opportunity to really make a difference and to say that here we are doing, not just being members of collaborations, but really being involved and making very important contributions and leading these big experiments that they are the future.
Yes, you're right.
So beyond the experiments, beyond the detectors, let me ask, gravitational wave astrophysics, what's the strongest thing you can do there? Who wants to take the ball?
The strongest thing in what?
Huh?
The strongest discovery that...
The most important discovery is the discovery that we don't know. I mean, in the history of astronomy, every time that we have opened a little band in the gravitational wave spectrum, there has been new discoveries. And gravitational wave is not a little piece more of this spectrum. It's not a new band. It's a whole new spectrum with properties completely different and complementary to light. Yeah. So the best is going to be whatever I cannot think today. Of course, with light, we cannot go back to the origin of the universe. With gravitational waves, well, maybe you can correct, I don't know, but you can have information from the universe when the universe does not even have a second. And the 10 to the minus 30-something, 40-something, I don't dare to know what to say because I will say it wrong. So there are many things.
Yes, I think that every time a new window is opened in astrophysics, there are unexpected sources. Starting from Galileo, the Jupiter moons were not predicted. So the pulsars were not predicted. So were not predicted the cosmic microwave background even, and so on. So now the gravitational waves already tell us that there are many more black holes that we expected, many more and even massive black holes. So, and this is only the beginning. So actually, the most, I think, beautiful surprises will have to come in the next years.
I mean, there have only been 3 science runs in these last 7 years. Just a few months integrating time of observation. 90 confirmed detection. This is nothing. In this next science run, we could be lucky, we could have several hundreds, but this is still nothing. When we go to space, to LISA, when we go to the future, to Einstein telescope, with Einstein telescopes, we are going to have millions of observations per year. Then we are going to do the same with LISA. We are going to do precision gravitational wave astronomy.
Yeah, for me, I think that there are challenges in the 3 areas. So, for instance, astrophysics, I think that for the detectors we have now, maybe they will tell us about the inner structure of neutron stars. So that will be a revolution. That's an example. For instance, in cosmology, they may provide the Holy Grail, which is this background in the same way that we have the cosmic background that tell us a lot about cosmology. There is a gravitational wave background there. Well, actually, there can be many of different origin, and detecting any of them can be a holy grail to understand much better the early universe. So, and then in fundamental physics, which is in particular I am biased because I think it's the thing I'm most interested. This probably more with LISA and Einstein telescope and whatever 3rd generation thing we have. Trying to understand whether the black holes are like we think they are, the structure of them, the way they behave. Also, whether they really merge in supermassive black hole merges in galaxies as we think they merge. So all this part we don't know anything because we have not seen this thing. And also the final probably goal in fundamental physics is going beyond general relativity, right? Is general relativity robust enough to describe all the detections we are going to do? So I think there are many things that are waiting for us to study in the next years.
Okay, we have to start wrapping up because we are completing our time of discussion, and we agreed to leave 5 minutes for questions. So 1 minute each. What would you tell a young PhD student that maybe is doing now gravitational waves, or maybe not, but who is interested in the field? What would you tell him or her for the next years? What is the prospects? What would you advise to them?
Well, the advice in gravitational wave always, no?
Yeah,
I mean,
yeah.
The one very two topics. One is this primordial black hole. Black holes formed when there was not yet a matter, no, just pure energy, and that could explain dark matter, for instance. That is fascinating, actually. And the other is, of course, the stochastic background of gravitational waves, which is the only access we have to the Big Bang, to the epoch of 10 to the minus 35 seconds. All the other probes, neutrinos, electromagnetic photons, are much later. So this is the other, the Holy Grail will be really to give a look to what happened at the Big Bang with gravitational waves.
Yeah.
Well, what I would tell to a young person is that this is an emerging field, it's an amazing field, and it's a multidisciplinary field. So here, it's not that you are going just to do one thing, you will be in contact with huge communities, astrophysicists, engineers, many different kinds of things. And that's amazing, and it's amazing to work in these huge collaborations worldwide. I think this is very rich. The environment, I think it's also nice. And it's really, I mean, it's going to still take many more years to do this precision gravitational wave astronomy. But I think that with gravitational waves, we are going to revolutionize the current concepts that we have about the universe, about the cosmos. And we are not a sect that we are working alone. We really need all of you, because we need to collaborate with all the other kind of observations, because the amazing part of this astronomy is going to be the multi-messenger astronomy, and to combine observations with neutrinos and with light in order to really try to answer many of the current open questions.
Yeah, well, I think, as they have said, I mean, I think there are many challenges ahead in order to realize the potential of all these detectors. So I will tell a student, first of all, try not to reinvent the wheel, because I think some people doesn't realize, as we said, this has a long history. There are many things that have already been done, but there are many other things that have to be done. And so I will say that every person has to find the area where they feel comfortable, like either instrumentation, data analysis, fundamental physics, modeling, whatever, and then look there at what are the problems, open problems that we need to be solved for the next 10 years, and yeah, go for it. And you know, I think there are many things to be done, and it's a very exciting field.
Yes, okay, to close the discussion, let me just mention that I like very much the analogy you did with Galileo, because for the first time he pointed something to the sky, and we started a process that in the last 200, 300 years has exploded. Maybe not so drastic, but maybe for the first time we have not pointed but run a detector on gravitational waves. Maybe in the next 50, 100 years, some panel will be here in the 200th edition of the IEEC forum or something, discussing, do you remember those old guys that were discussing gravitational waves? Look at what we did after so many years. That's a challenge for you to leave for your successors to organize a panel in a long time. So, okay, we have how long? 5 minutes for questions, less?
Not even that.
Not even that.
Yeah.
Couple of questions?
Yeah.
Couple of quick questions from the audience. Somebody in the back?
Hi? Yes. Well, first a comment. Maybe you should have mentioned on the issue of new discoveries that there was not just the discovery of the gravitational waves, but the discovery of black holes of a few, so to say, tenths of solar masses. Those were supposed to
But
be
the
not
chairman
there.
is very strict with the time.
Yes. Well, okay.
My fault. I can take the full blame of that.
Yes, and then a genuine question. Yeah? Can you predict how far are we from detecting primordial gravitational waves?
From detecting?
Oh, how
Primordial.
far we are in order to detect primordial gravitational waves?
Okay.
Well, do they exist? Do they not exist? Which mass range are we talking about? Very small, very large, depending on the mass range, they are going to be in different frequency bands, so they will be target for us or for space. But in any case, if we see or we don't see them, or we can classify them as
I think at least we have to wait for LISA and ET,
ET.
to be
I mean,
on
with
there.
ET,
So
with
at
ET
least
we will be seeing
10 to
until
20 years.
we will see
Well,
Z10,
actually,
Z20.
There was an announcement in 2014 of some people that have an experiment in the South Pole. Was measuring the polarization of the CMB, the cosmic background, that said that they have detected the imprint of the primordial gravitational waves in it. Then they did a big announcement. It was very embarrassing because then realized that they have confused the effect with the effect of interstellar dust. But these experiments are improving. So because this is a very speculative physics, we don't have predictions at which level are going to appear, right? So you can do the best instrument you may think of, and still, we don't know at which level they are going to appear. But at the level it appears, just this information is a huge information. Right?
Thank you. Just one quick last question from the audience. Or no question, that. Anna.
Working? Yeah. Thank you for this interesting panel. And I have a curiosity. How do you synchronize all the information between all the detectors and the collaborations when you are about to detect, or you have the suspicions that you are about to detect gravitational waves? So how do you manage to collaborate with so many groups?
I don't understand the question. You mean
Fine,
how
there
we
is-
pass the
You-
information or how we pass that we don't leak information?
No, if you
Because
are
they-
working together, Virgo,
Well, they keep us with a
LIGO.
very military discipline, completely organized, and then how to report things. And for example, even the announcement of the first discovery, there were even a rehearsal 2 years earlier. And because we also do injections and so on. So everything was trained from the beginning to the end. So who does what, all the checks, then everything is recorded. There is some low latency analysis in which you record everything on the database. I mean, today we can check how many, if we have more detections. Oh, the 2 LIGOs are on today, so there could be already maybe a detection today, and that this has to be analyzed and so on.
and you have
and-
to react in a very short time. Right?
It depends. Well, you have to send the alerts. Because now the alerts are open. Not much information there. So there are many different kinds of things. And then you have all the checks. And then the checks, you have all these working groups very well structured. And then you collaborate with different working groups. I mean, maybe you are compa binary of a certain type that you are doing this a certain analysis. But then you have to talk with experimentalists and with the detector characterization working groups to really to make sure that everything was properly done, and to the calibration working group. You might need to do some recalibrations to really reanalyze the data in order to really extract the best information you can.
Thank you. Yeah, I think that I will take a moment to close the session.
Thank you.
So, well, thank you.